I want some points. How easy is that? And what I'll do is we'll kind of talk about where you're at, what needs to happen to the file, kind of an end game thing as far as the course goes. So 3 points, please do this. You have to do it before the day of final exam, so that I can give you appropriate credit. Also, there's another bite at the apple. Obviously, this is the time of the year for course evaluations. Please do these. If I get 90% or better of you responding, obviously I don't know who responds, but I hear tells me what percentage of people responded. If I get 90% or better, everybody gets 300 another clip. So that has to be done. That has to be done by the close of business on the day of the final exam. So you can pick it up if you want. Just don't get to it. Okay, any questions? Okay, so I had promised this before. We're going to do something called there's actually a proof in the text, if you like, of why this works. I'm going to give you something a little bit more fast and a little bit more heuristic, but this is the way to okay, so what this is, Gram-Schmidt process is just a way to take a basis. So maybe I give you a basis that's really kind of crappy, right? It's not very useful. You can take that basis and you can do a little mathematical prestidigitation to it, massage it a little bit, and make an orthogonal basis come out of it. Or you can even up the voltage and make it orthonormal. By the way, somebody remind me, what's the difference between an orthogonal basis and an orthonormal basis? Yeah. Orthonormal basis are like normalized on the same line. That is correct. So orthogonal just means that any two different ones are perpendicular to each other, right? Orthonormal means that and the length of each vector in the basis is exactly one. So if you do an orthogonal basis, you can always do an orthonormal. Now, believe it or not, you already know how to do this for small stuff, right? So let me give you an example. Here's one from the exam. Of course, you don't need Gram-Schmidt, you just need what we did before. Let me give you two vectors here. By the way, these two vectors are linearly independent. It's fairly easy to test this, right? And I gave you this question here, and I didn't ask it to, but you can actually get a normal basis. Notice that U and V, they're linearly independent, so they span a two-dimensional subspace of R4, right? And I think I asked you a question. I said, find a vector in W that is orthogonal to U. Y'all remember that question from the test? Find something in W. So how do you do this? Well, this is nothing more than this projection stuff that we did before. So let me just kind of draw a picture just to get perspective. I want something in the space W. Now W is spanned by two vectors. So basically the chalkboard is now my space, right? Now here's U and V. Are these two orthogonal as they sit? No, they're not. And you can test that by doing the dot product, right? The dot product of those two is 6. Okay, they don't sit at right angles. So this makes me very sad because I want something in here that sits at a right angle to you. Right? How can I do it? Well, how about this right here? That yellow one looks like it's at a right angle to this, right? And what is this? This is V minus U hat, where U hat is this kind of shortened version of U here, the projection. Right? So this is an exercise in these kind of old projections. Everybody okay with that? The V minus U hat we know how to get. Let's get U hat. Well, that's just a projection of V onto U. So U hat is, let's see, V dot U is going to be 6. U dot U is 3. And U itself is, so I get this U hat should actually be 2, 0, 2. And so this thing should sit at the right angle. This thing right here should be and what would be was 0, 1, 2, 4 minus U hat. So it's like minus 2, 1, 0, 2. There. Now, a lot of you on the test got some points for finding something that's orthogonal, but many people gave me something that was orthogonal, but it wasn't in this plane, right? There's lots of things that are orthogonal to you, but probably what you got is not something in the plane, it's something stuck out, right? You've got a lot of freedom about that. The whole plane stuff is more than that. It's orthogonal to you, right? But this has the property, notice that you can check this is orthogonal to you, right? Because if you take the dot product, you get 0. And it is also a linear combination of V and U hat because it's actually V minus this number times U, so it's in W. I agree with that. And then after that, I said, okay, find me something that's orthogonal to you. Now it said find an orthogonal basis. Right? Okay, so how am I going to do that? Yeah,
Just U and then the B minus U.
that's right. So, in other words, and what if I wanted to make it orthonormal? Just divide out by the length, right? So and the length of this is 4, 8, 9, so it's a perfect 3. And there is a orthonormal basis for two-dimensional space. So we already knew how to do this. Now, how do we generalize this, right? I mean, what if I've got a larger space here? Let me do kind of a bigger, which will kind of be a lead in to how the Gram-Schmidt process works. So here's kind of Here's kind of my challenge problem here. Construct. Construct. Orthonormal. Basis. Or W. And what is W? The subspace of R4. Stand by. Let's go 1, 0, 1, minus 1. I'm going to call this X1. X2 is 1 minus 1, 0, 0. And X3 is 1, 0, 1, 0. Now I'm going to go through a process where I'm just going to key on this. I'm going to order. I'm going to construct a new orthonormal base. So W is find the span of X1, X2, and X2. Now, this is very similar to the example we did before. We just build this up piece by piece, right? Let me point out, just to be careful at the very beginning, it's very easy to check that these three vectors are in fact linearly dependent. There's three of them, so they span a three-dimensional subspace of R4. So it's not going to be all of R4. It's just going to be a piece of it. What I'm going to do is I'm going to start off, and just because of the way I numbered this, I'm going to start off with this element part. This is going to be one element of my basis, period. And I'm going to call this, since I'm making new elements, I'm going to let V1 be X. I mean, renaming my new basis. So there's the start, right? That's a non-zero vector. I can start with any when I want, and that's going to be part of my orthonormal basis, right? If I wanted to make it easier on myself, I might have started with one of these, but I'll do it. Now, what you want to do is there's your first basis element. It's already orthogonal to everything else because there ain't nothing else, right? So now we need to find the second basis element. We're just going to build this up like a ladder. The second basis element is the same idea as the problem we just did. All I have to do is just find something that's orthogonal to this. Same principle here. This is V1, the one we started with. And so we're going to take the second original basis element, X2, and project on it and do the same thing. Okay. So I am going to have V2 be V1 minus V1 dotted with X2 over X2 dotted with X2. I'm sorry. This is there we go. Yes. So this is the same process that I went here. I took X2 and projected it onto V1, and then I subtracted off those two. And we'll take a look at it and make sure that it is indeed orthogonal. Come out of this to the original vector. Let's see what we get here. Let's see here. V1 dotted with X2. Okay, let's see. What is V1 dotted with X2? It's just one, isn't it? Right? Because you have a 1 here and then zeros all the way down. Right? So this is 1. And B1 dotted with itself should be should be 3, shouldn't it? If I agree with it. So what I should get then is x2, which is 1 minus 1, 0, 0. And then I subtract off 1/3 of B1. So that's 1/3, 0, 1/3, minus 1/3. And I get the vector, let's see, 1 minus 1/3 is 2/3. Minus 1, 0 is 1. 0 minus 1/3. And 0 minus 1/3. Everybody okay? Yes.
Shouldn't the one be a negative one?
Let's see, which one are we talking?
You did -1 minus 0.
Thank you. Did I get it right now? Is that what you meant? Okay, yeah, I agree. Everybody okay? Now, what I'm going to do here is I am going to take I'm going to go 2 minus 3 minus 1. What is the relationship between this and what I got from my answer up there? It's just a multiple, right? I just multiplied this by 3, right? Why did I do it? I certainly don't have to do this, but I would rather work with integers and fractions than you. It just makes my life a little bit easier. Right. So I'm going to take B2 to be this. So now I've got B1 is equal to 1, 0, 1 minus 1. B2 is equal to 2 minus 3 minus 1, 1. And notice, this is certainly in the space generated by the first 2 vectors, and notice the dot product of these 2 sequences, so they're right angles. Everybody okay with that? Question. Okay, so I haven't done anything different in principle than I did at first, but now, right, this is where it gets different because last time I didn't have to go over 3 vectors. Okay? But the principle is the same. Third basis element. How do we build B3? Remember, this is a 3-dimensional vector space. If I'm going to build more orthogonal basis, better have 3 things in it. What do I do now? Well, now it's really, in principle, not that much different. B3 is made from X3, just like B2 was made from X2. What do you subtract off? Well, what you have to do is you have to make sure that this guy is perpendicular, not just to B1, but also to B2. So you project X3 onto these 2 other things that you've already gotten and go down with it. The formula is the same. So this should be X3 dotted with B1 over B1 dot B1 projected on the B1. X3 dotted with B2 over B2 dotted with B2. So as I said, in principle, it's not really different. What happens is you have to start with your C to X3. This right here, when you subtract off, guarantees you that you're going to be orthogonal to B1, and this gives you orthogonality. Right? The principle is the same. Instead of just taking into account one vector, you have to take into account all the preceding vectors and project onto them make it perpendicular or orthogonal to everything. So let's see how this works. Let's go through this. So let's see what happens. Let's see. I need x3 dotted with b1, and that looks like it's going to be a 2, right? And b1 dotted with b1 is 3. Everybody okay with it? For the second multiplier, I need x3 dotted with b2. Where do I get there? Well, I got x3 and b2. Yeah, I get 1. And b2 dotted with itself, I guess, is 15. So let's see what I get. This is going to be x3, which was 1010 minus 2/3 b1. Okay, so we're gonna have 2/3 this one. So it's gonna be 2/3, 2/3, 2/3. And 1/15 this thing, which is unfortunate, but read the first here. 2/15 minus 3/15 minus 1/15 plus 1/15. Let's see if we can do this here. Let's see, 2/3 and 2/15 is 12/15, which is 4/5. So 1 minus 4/5 is 1/5. Or 1 minus, yeah, 4/5 is 1/5. That's going to be a 0, 0. That's going to be plus 3/15. This is going to be, let's see, that's going to be minus 10/15 plus 1/15, which is minus 9/15. So it's minus 3/5. 1 minus 3/5. 2/5. Right. So I am. And that's going to be plus 2/3 minus 15. So that's going to be 10/15 minus 1, 9/15 plus 3/5. And so I'm going to take B3, I'm going to scale this, get rid of this 1/5, 1, 1, 2. And so if I take B3 here, I already checked these two are orthogonal, or these two are orthogonal. Let's see, we get 1 and 2 is 3 minus 3. Okay, these two are orthogonal. How about these two are 2 minus 3 is -1, -3 plus 3. So there's your orthogonal basis. To make this orthonormal, so B1, B2, B3 is an orthogonal basis. And of course, to make it orthonormal, just divide by the length. And the length of the first one, right, 3. The length of the second one is, I guess, square root 15, right? So 2 radical 15 minus 3 radical 15 minus 1 of radical 15 and 1 of radical 15. And finally, our last one, the length of this is 9, is again radical 15. And this is what the norm basis for. The Gram-Schmidt process always builds a set that's sort of orthogonal. And the cool thing about it is, I think probably if you looked at it at the start of the problem, it's probably easier to tell linear independence, that these three are linearly independent. It's a little bit tougher to tell that these three are linearly independent, but I know that it has to be a linearly independent set because it's orthogonal, right? Any orthogonal set is linearly non-zero. And those of you out there, I think it would be a legitimate criticism to say, you took a perfectly good looking basis here and turned it into a pile of crap here, right? I mean, I think that I would have to agree that that might be, sort of a decent criticism. However, orthonormal bases, depending on what your problem is, what space you're looking at, what thesis space you're looking at, this could actually be a much better basis than this, depending on what your situation is. It's just like an analogy might be when you look at polar coordinates, right? In Cartesian, is a circle a function? It's not, because you draw a vertical line through parts of it to get it in more than one point. How easy is it to integrate the square root of r squared minus x squared, right? And find area inside a circle, you have to consider the upper and lower. However, in polar coordinates, the circle is a constant function, right? It's r equals 1 if its radius 1, r equals 2. And so, even though the spaces may look worse, sort of in standard coordinates, the coordinates where you're doing a particular problem, it might be much better. And the good thing about it is, it's an orthonormal basis. You can completely determine coefficients very easily by using the dot product. Okay, so let me. So now that we've worked through these examples, let me give you sort of a general form of management process. This is kind of the theorem that goes with it, and you will see it's exactly like these examples here. So, there. And I was going to help Gram-Schmidt process. Given a subspace W and Rn for the basis let me point out, so suppose I've just got some random subspace Rn with basis x1 up to xk. So what I'm saying is W is a k-dimensional subspace of Rn, which of course means that k is less than or equal to infinite. You can't have a 10-dimensional subspace with 3-dimensional vector. Suppose we've got this basis, and this basis can be refined this would be exactly the process that we went through. Whatever this first basis element is, let that be V1. Now make V2 by projecting X2, we're subtracting off X2, projection on V1. Do X V3, just like we did before. Okay, so you take X3 and when you subtract out, you've got to project X3 onto all the former basis elements, the ones that you've already got. Uh, Here, I'll do one more just for clarity. C4 is X4 minus, okay, now I gotta project X4 onto all the previous ones. And the last one, dk, of course, is xk minus xk vector on B1, 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 B1 minus finally xk vector dk minus 1, dk minus 1, dk minus 1. So this is the process, right? You just, and of course, you see why it's called a process, because you start B1, make the next one, take the second element, and take off the projection, make the third element, take the third original element, take off all the projections on the previous ones, and just keep going like this. Then B1, B2, dk, these new vectors that you discovered by running this process, so B1, B2, all the way up to BK is a new improved, not just basis, but an orthogonal basis. And of course, you can now take these animals here and make them an orthonormal basis if you just divide each one out by its length. Okay, any questions? Is there any points of clarity about the way the process works? This is not a difficult process. It looks daunting when you write it down, but I think if you practice a couple of examples, you'll kind of, it's kind of very algorithm driven here. Let me give you another application. Here's one application and we're going actually we'll see some more, especially when we get to the next section on different product spaces. Okay, so let me describe the type of matrix we're going to be looking at here. There, and I'm going to call it QR factor. Let's suppose that okay, suppose I have a matrix It is in rows by in columns, so this is not necessarily a square. Any rectangle matrix. But here's the caveat. There's a catch. I do need something. With linearly independent columns. Then A can be written in this form. It's the name QR factorization. But let me tell you, you got to take what Q and R are with Q. Q is a matrix of the same size as A with orthonormal columns. And here I do mean orthonormal columns, I don't just mean orthogonal columns. That is another way to think about this is column form and a orthogonal basis. Or I'm sorry, orthonormal. Or column base bay. Or column. And R is and what is R? R is an n by n. Invertible upper triangle matrix. I'm going to go through an example and explain why it needs to turn out this way with positive entries in the diagram. And in fact, you can set it up. Yes,
Why specifically does Q need to have orthonormal columns?
because otherwise it won't work. So, I mean, it has to have orthonormal columns to make that multiplication work. And when we do it, I'll show you where the orthonormal actually is what makes it an upper triangle matrix. Right? Because notice, I didn't just say it was an invertible matrix. It could be just an orgy of numbers. It's just a huge mess, right? It's actually upper triangular. And not only is it upper triangular, it's got strictly positive elements on the diagonal. That's where you need your orthonormal. And we'll see this, I hope. Tell me if you don't, but hopefully you'll see this when we do the computation. So let me do an example. Let me do an example of what I worked out, and I want to show you something that's kind of interesting. Example. Okay, so and here's why it's an application. So this will allow me to do Gram-Schmidt. And actually, I got to do it set up here. So let's let A. One. Okay, so now I'm gonna attempt to do a QR factorization of this. I'm following my notes here. Well, the first thing is, though, I mean, technically, what do I need to know about A in the first place before I even know that I've got a kilo of factorization? You need to know that those columns are linearly independent. They sort of look linearly independent to me, but actually, here's what I'm going to do. Instead of going through and hardcore testing that these columns are linearly independent, I'm going to do the Gram-Schmidt process. What do you suppose would happen if I do the Gram-Schmidt process and they're not linearly independent? At some point, I'll get zero back. Like the Gram-Schmidt process will essentially fail to do something new. So let's just test this out. Let's go X1 is the first column. X2 is the second column. And X3 is the third column. Now, if I run the Gram-Schmidt process and get three non-zero vectors, I know that those three non-zero vectors have to be linearly independent because they're orthogonal, right? So I am going to trust in the force for now and hope that the Gram-Schmidt gives me three non-zero vectors. So let's see what happens. So what I'm going to do is I'm going to take the columns in this, and I'm going to turn these columns into orthonormal columns. Right? So this is just straightforward. Let's do Gram-Schmidt, see what happens. So okay, so I'm just going to take B1 as X1, which is 1, 1, 1, 1. Okay, so I've already got that done. B2 is, let's see, X2 minus, I've got to project that onto everything I've discovered so far. Let's see what happens here. This is X2 minus some crazy fraction times V1. And let's see, what do I get here? X2 dotted with V1 is, oh, I'm the luckiest guy in the world. What does that mean? That's right. In particular, the vectors I was looking at were orthogonal already, right? So this is 0 over who cares, as long as who cares is 0, which it ain't. And this is just X2. So that was a brush of good luck. All right. Orthogonal so far, and finally the last two. Let's see, X3 dotted with V1, or V1 dotted with V1. And now let's do it here. X3 dotted with V2, V2 dotted with V2. Okay, so let's figure out what the fractions are. Okay, let's see, X3 dotted with V1. See where's X3? There you are. Dotted with V1 is going to be 4, right? 4. And V1 dotted with itself is 4. So let's just do 1. Now, X3 dotted with V2 is going to be, this was going to be -2, -4, total -6. Looks like it's -8. And V2 dotted with itself is also 4. So this is X3 minus V1 plus 2 V2. And let's see if we can start to go ahead and get this. X3 is -2, and then -1 plus 2, so it's gonna be, that's gonna be -1. That's gonna be -3, -1, or that's gonna be total -3. Okay, good. The next coordinate should be 4, -1 is 3, -2 is 1. The next coordinate should be 2, -1 is 1, -2 is 6. Uh, 2 -1 is 1. This is -1. And finally, the last one is 0, -1 is -1. So I get this. Now, these two are orthogonal, as you see. This one is orthogonal to this, that's clear, and it's orthogonal to this, it's -1, so it's -2. Now, these vectors are orthogonal, V1, V2, and V3, right? But they're not orthonormal. What are the lengths of all, actually, it's convenient, what are the lengths of all of these vectors? They're all of length 2. Correct. So I want to build Q this way. So Q is created by orthonormal basis. For column A. I took the columns out of A and made an orthonormal basis. Let's put them back in order. And the next is 1/2 minus 1/2 minus 1/2 1/2 plus half of V2. And finally, it's minus 1/2 1/2. So there's your Q. That's the animal that has orthonormal columns. How about R? So it's got to be a 3x3 make. Yes.
All of the diagonal values are just going to be 2.
Well, we'll see. We'll figure out. I can figure out what R is just by computing, right? Because and you were asking about what's the importance for the label. This is why. This is one of the reasons why. What I've done is I've multiplied this equation on the left side by the transpose of Q. Since Q has orthonormal columns, what does QT times Q turn out to be? Q is, by the way, 4x3, and this is 3x4. This turns out to be 3x3 identity matrix, right? That's exactly the point of the orthonormal columns. So R is equal to QT A. And so we can figure out what R is. It should be 3x3 this way. QT is, QT is 1/2, 1/2, 1/2, 1/2. 1/2 minus 1/2, 1/2, 1/2, and minus 1/2, 1/2, minus 1/2, 1/2. And A was this original. 1, 1, minus 2, 1, minus 1, 4, 1, minus 1, 2, 1, 1, 0. And when I multiply this out, this row comes this column, 2. This row comes this column, you get a big fat 0. This row comes this column, you get minus 1 plus 2 is 1, and 1 is 2. Now, here's another place where the orthonormal columns come in. This column times this column, they sit at right angles, so I promise you, you get a 0. And in fact, until it hits the second column, it's hitting stuff that's perpendicular. And so, let's see what we get. When we get here, we get 1/2 and a half and a half and a half and again. And here times here is minus 1, minus 3, minus 4. And finally, again, this row now, this is orthogonal to this. So I guarantee you 0. This is orthogonal to this because that's what Gram-Schmidt did for us. 0. And finally, this is 1 and 2 is 3, minus 1 is 2. So your prediction is correct as well. Okay. Any questions? By the way, let me give you a little puzzle here. When I put this together, when I made this example, I had I built this from starting with the Q and the R. And I made this Q the negative column. So it was almost like this. It said negative, negative. And R had a minus 2 plus 4 and a minus 2 here. That's how I built the A. And when I took it back apart, it made this positive. You might ask yourself why it fixed it to make positive values on the diagram. Okay, question. Yes,
When will our next quiz be?
your next quiz will be Friday. Any questions? All right, I will see you all on Wednesday.